Welcome to this Maths Made Easy video on implicit differentiation. To start with, let's take a look at a method for implicit differentiation. So to carry out implicit differentiation, we need to follow these steps. So step 1, we differentiate terms that are in x only. For step 2, we use the chain rule to differentiate terms in y only. So what would that look like? Well, that would be the derivative with respect to x here of f of y. And this would be equal to d by dy of f of y times dy by dx. And this is just the same as differentiating f of y normally and then multiplying by dy by dx. And for step 3, we use the product rule for terms that are in both x and y. So if we have d by dx of u of x v of y, then in that case this would be equal to u of x times d by dx of v of y plus v of y times d by dx of u of x. Okay, and you can use the rule in step 2 to find d by dx of v of y there. And finally, for step 4 then, we rearrange the resulting equation to make dy by dx the subject to obtain our correct differential there. So that gives us everything we need there for a method for implicit differentiation. Moving on now to take a look at finding the gradient with implicit differentiation. So with implicit differentiation, we can still find the gradient just like we would with regular differentiation. And we can calculate the gradient at a given x value by finding the y value from the equation for the curve, and then simply finding dy by dx at these values of x and y. We can also find other things, such as an equation linking x and y at stationary points dy by dx equals 0. So if we take a look at this example here, we're told a curve is defined by y squared minus 3xy plus x squared equals 0. We want to find the gradient at all points where x equals 2. So here we need to differentiate implicitly. So if we go along term by term here, well, this y squared, so if we differentiate here, implicitly this would give us 2y. So that's 2y. Remember, we need to multiply this by dy by dx. So that's 2y dy by dx. Okay, so 2y dy by dx. For this minus 3xy here, for this part, we need to use the product rule. Okay, we need to use the product rule. So if you use the product rule here, what you're going to get is minus 3x times dy by dx. So this is minus 3x dy by dx minus 3y. Okay, so if we differentiate here minus 3xy implicitly, this is what we get. We get minus 3x dy by dx minus 3y. And finally then, x squared here would just simply give us plus 2x. Okay, and this is still equal to 0. So here now what we want to do first is find dy by dx. So to do that, we need to rearrange. So the first thing I'm going to do here is factor out dy by dx. So I'm going to get the 2y minus 3x. So 2y minus 3x dy by dx. And that's going to be equal to 3y minus 2x. Okay, so that will be equal here to 3y minus 2x. Okay, just taking this part here onto the other side. And therefore, if we want dy by dx, notice here we just need to divide here by 2y minus 3x. So therefore, dy by dx is simply given by dividing the left-hand side and the right-hand side here by 2y minus 3x. So that gives us 3y minus 2x all over 2y minus 3x. Okay. So now that we've got dy by dx, all we simply need to do here is substitute the x value into the curve to find the y values. So at x equals 2, so x equals 2, what we've got then is y squared minus 6y plus 4 there. Okay, 2 squared would give us 4. So what that tells us then is y squared minus 6y plus 4 is equal to 0. So therefore we can now find y, and in this case y is simply equal to, and using the quadratic equation here because we can't factorise this expression, that would give us minus 6 plus or minus the square root of b squared, minus 6 squared, minus 4 times 1 times 4 there. Okay, remember we divide this by 2a, and in this case a is 1, so we divide this by 2. And here we just need to start simplifying here our numerator, so we get y is equal to 6 minus 6 would give us positive 6 plus or minus square root of 36 minus 16 all over 2. And we can simplify this here to give us 3 plus or minus the square root of 20 over 2. The square root of 20 divided by 2. And in that case then, that would simplify here to give us 5. So this is equal to 3 plus or minus the square root of 5. Okay, so y is equal to 3 plus or minus the square root of 5. So here now, we need to substitute x and y values into dy by dx. So what we've got here is two possible options. We've got y equals 3 plus root 5 and y equals 3 minus root 5. So take note here of x equals 2 and our values for y here. What we're going to do is just clear this ink on the screen so far and then carry on with the question, because it's quite a lengthy question here. So if we carry on now, all we need to do then is just substitute the x and y values into dy by dx. So when y is equal to 3 plus root 5 here, okay, so y is equal to 3 plus root 5, well in that case, dy by dx here is going to be equal to 3 times 3 plus root 5 minus 2 times 2 there. Okay, so minus 2 times 2, and this is all over 2 lots of 3 plus root 5 minus 3 times 2. Okay, so here now we need to simplify this. So the first thing I need to do is simplify the numerator. So we'd multiply 3 by this bracket here, so that's going to give me 9 plus 3 root 5. Okay, so I get 9 plus 3 root 5, and 2 times 2 is 4, so minus 2 times 2 will give us minus 4 there. Okay, that's minus 4, so that's the numerator simplified. If we repeat this process then with the denominator here, 2 lots of 3 will give us 6, and 2 lots of root 5 will give us plus 2 root 5. Okay, and then finally minus 3 times 2 will give us minus 6. Okay, so if we simplify here, we can notice straight away that that 6 will cancel with this minus 6 here, so we're just going to get left with 2 root 5 in the denominator, and 9 minus 4 will give us 5. So what we get here is 5 plus 3 root 5 all over 2 root 5. Okay, so 2 root 5. And here now what we want to do is just rationalise this. We want to get rid of this third in the denominator. So if we start doing that, we're going to times top and bottom here by 2 root 5. And if we do that here, what we get for dy by dx is 5 root 5. So I get 5 root 5 plus 15. Okay, so 5 root 5 plus 15, and that's all over 10. And then we can simplify this one step further here. So what I get here is 3 plus root 5 over 2 there. Okay, so dy by dx is equal to 3 plus root 5 over 2. But that's only for when y is equal to 3 plus root 5. We also now need to repeat this for y equals 3 minus root 5. So let's clear all this and repeat this one more time with y equals 3 minus root 5. So if we eliminate that ink there, and we carry on with this then, now considering y equals 3 minus root 5. So y equals 3 minus root 5 here, again, just substitute x and y values in, so remember x is just simply 2. So dy by dx is simply given as 3 lots of 3 minus root 5 minus 2 times 2, and this is all over 2 lots of 3 minus root 5 minus 3 times 2, and it will follow in a very similar fashion to when y was equal to 3 plus root 5. Again, simplifying the numerator here and then the denominator. Well, 3 times 3 is 9, and we get minus 3 root 5. We still get minus 4 here, and for the denominator, 2 times 3 is 6, and we get minus 2 root 5. And again, we get our minus 6 there. So straight away, again, 6's will cancel in our denominator. We've got 9 minus 3 root 5 minus 4, so that's going to give me 5 minus 3 root 5 all over minus 2 root 5 here. Okay, so again, we just want to start simplifying here and rationalising the denominator. So in that case, if we rationalise here, we get dy by dx, and that's going to be equal to 5 root 5, so 5 root 5 minus 15 all over minus 10 there. Okay, and again here, just simplifying this one step further then, for dy by dx we get 3 minus root 5 all over 2. Okay, so that's dy by dx. So therefore, the gradients at x equals 2 are 3 plus root 5 over 2 and 3 minus root 5 over 2. And that gives us everything we need there for finding the gradient with implicit differentiation. And finally, let's take a look then at differentiating the inverse trigonometric functions. Implicit differentiation is how we find the derivative of arc sine, arc cos, and arc tan. So if we take a look at this example here, we want to find the derivative of arc sine of x. So let's rewrite this as y equals arc sine of x. So here now what we're going to do is take sine of both sides of this equation. So that's going to give us sine of y. If we take sine of arc sine of x, that would simply give us x. And now what we can do is differentiate implicitly. So in that case, if we differentiate the left hand side here, that's going to give us cos of y. And then remember, as this is in terms of y, this would be multiplied by dy by dx. So that's cos y dy by dx. And this is equal to the derivative here of x with respect to x. That would give us 1 there. So we want dy by dx. So what I need to do here is divide by cos y. So therefore, dy by dx is equal to 1 over cos of y. Now we need to do a bit of work here to get this into a form that looks more familiar. So cos of y, we could write that as the square root of cos squared y. So therefore, dy by dx is equal to 1 over the square root of cos squared y. What we can do now is use our trig identities here. We know sine squared y plus cos squared y is equivalent to 1. So in that case, if we've got here the square root of cos squared y, well, we can write this then as cos squared y is equivalent to 1 minus sine squared y. Okay, and in that case, we can replace them, our cos squared y, with 1 minus sine squared y. So this is equal now to 1 over the square root of 1 minus sine squared y. Okay, now we know x is equal to sine y. So in that case, if we know x is equal to sine y, 1 minus sine squared y is the same as 1 minus x squared. So this is equal to 1 over the square root of 1 minus x squared there. Okay, and that gives us dy by dx there. So that gives us everything we need there for differentiating the inverse trigonometric functions, and that concludes this Maths Made Easy video on implicit differentiation.